So welcome everybody, my name is Ralf Kaegi, I'm working for Ralf, that's the Swiss Federal Institute for Water Science and Technology, and I've been involved in the nano business for quite a number of years now, mainly focusing on the fate and transformation of the nanomaterials in the urban water cycle, especially the wastewater treatment plants and related systems. So Lars gave me the task of talking a bit about nanometrology or metrology, and I just could show you all the data, all the methods which are available. However, I thought this is a bit boring, and I just will show you based on a case study. I will introduce some specific analytical techniques that we can use in order to assess and try to quantify and assess the nanomaterials, engineered nanomaterials in complex environmental systems. Now, you often hear the statement that we can't measure engineered nanoparticles because they're so small. When here I have a table, and it's not the newest table anymore, but you'll find comparable tables in all reviews and book chapters. I don't want to go through all the methods, but you see there's a lot of methods, and just highlight here, that's the size. You see that's 1 nanometer. There's plenty of methods which go into the nano size range and even below. So I think we're fairly good in characterizing materials at the nanometer scale and even below. But the question is, the fundamental question is, that's also where the challenges come from. Can these methods be applied to nanoparticles in complex matrices, such as food, in cosmetics or in sludge? And that's where we want to quantify them. The answer, you can guess, probably not. There's the challenges. What are the challenges? The major challenges are, for sure, we have only low concentration of engineered nanomaterials in these complex matrices, because if you think about a surface water or groundwater, there's plenty of materials there which are already in the nanoscale, and if you go through a bit of the older literature, you find data of reporting concentrations of nanoparticles, natural nanoparticles in the order of 10 to the power of 11, 10 to the power of 12 particles per liter. Second is the similarity between engineered natural and incidental nanomaterials. You have to identify, you know the natural particles are there, and then you also have to be able to distinguish between the natural particles, the incidental particles, and engineered nanoparticles. Just to give you a few examples, silver or copper metallic nanoparticles can be synthesized by the green root. That means bacteria or plants. They produce metallic nanoparticles. You cannot distinguish them from engineered nanoparticles, which are synthesized on purpose. Another example of welding fumes, which produce perfectly spherical particles, metallic particles, which will be hard to distinguish from engineered materials that have been synthesized on purpose. And last but not least, and Greg probably likes this, these associations between engineered nanoparticles with natural colloids, and that makes things, at least the transport of the engineered nanomaterials, fairly easy, because you often find the nanomaterials associated with larger colloids and not dispersed in the nature. But maybe Greg talks a bit more about this. So if you have all these challenges, we basically can summarize this on this slide here. And where we are is this: we are in a lab system where we have all equal particles of all the same size in a monodispersed size distribution. Then we can apply virtually all the techniques that I showed you in the beginning in this introductory slide. We can measure some properties and extrapolate them to all of the particles because they're all the same. However, if we move towards an environmental distribution, towards a complex matrix, we first go to the industry batch, and there we don't have monodispersed particle size distributions. We more have polydispersed systems, and then already light scattering techniques break down. We have the products. We release particles from the products, and in the end, we have an environmental distribution where we may have individual engineered nanoparticles, but we have a lot of other particles like clay particles, iron oxide, organic materials, and depending on the particles, we may have also a partial transformation of these particles in the environment. So in that case, we only need to determine one parameter, but this is valid for all others. In that case here, you need to have a size information, you need to have an elemental information, and you need to have a structural information to fully characterize and quantify materials in environmental complex matrices. Now, there's two conceptual approaches how we can solve this. how we can solve these challenges, or we can address these challenges. This is our system here, the complex system. We can either go clockwise or we can go counterclockwise. Clockwise means that we first try just to disperse the particles using ultrasound treatment, using dispersion agents, using selective dissolution of matrix components. Now we have this system here that won't work in practice, but in theory, as a thought experiment, it is fine. You have well-dispersed particles, and then they have different sizes. And then you need a size fractionation. A size fractionation, you can, for example, use a hydrodynamic chromatography or a field flow fractionation. And this basically separates individual particle classes into close to monodispersed size distribution, as schematically shown here. And during the elution of these experiments, the size distribution unfolds along the time axis, and in theory, it would be nice if we have just the engineered materials then concentrated in one of these size fractions, which then can be analyzed with methods that we have currently available, because we have separated the particles into close to monodispersed size fractions. And then we come up with a particle size distribution of the engineered nanomaterials. The other approach, and I will focus on that in the case study I will present, is that we use complementary analytic techniques and don't really care about the complex matrices. And we just first determine, for example, the bulk element concentration, and then we know how much that we have in the system. Then we go to the electron microscope and we determine how do the particles look like, and in combination with the bulk methods, we may derive a particle number concentration. And if required, for example, the case when you have reactive nanomaterials, for example, silver, you may have to go to a synchrotron absorption spectroscopy method to determine the speciation of the individual particles. If you combine then all the methods, which are bulk methods or individual particle methods, you eventually or hopefully come up with the same particle size distribution. Now, I'd like, just based on my case study, I'd like to pick some what I think relevant, and for sure this is a biased selection. I pick some relevant analytical techniques, and I show you how to apply them based on this case study. Important is that we always have a question. We have to ask a question, and based on these questions, we choose the analytics. Unfortunately, today it's often the other way around. You have an analytic, and based on the analytic, you define the question. But I think this should not be the case. So in the first, I will show you some data about the release of nano-titanium dioxide, possibly nano-titanium dioxide particles from landfill sites. We wanted to assess the bulk concentration. For that, we used ICPS. Then we wanted to get information about individual particles. We used electron microscopy, and I'll talk about more in a few slides. And we wanted to get the number concentration of the nano-sized titanium dioxide particles. For that purpose, we used the single particle ICPMS method. Just a few words. The study site that's shown here. It's a northern part of Switzerland. It's a northern part of Switzerland. That's the landfill site. It's construction material. That's a manhole here. Sampling site is here, where we collected samples over the course of a year. First, to come to the titanium concentrations. As I said, we used ICP-OS and ICP-OS methods to get the bulk concentration in the effluent of these landfills. And you see, you have, that's a log scale here. You have to be careful. But you normally have concentrations in the order of a few tens of micrograms per liter. And that gives you kind of an indication we have titanium leaking from this effluent. If you don't find any titanium there, you can stop it, and you don't need to look for any nanomaterials. The interesting thing is now, if you correlate the total suspended solids with the titanium concentration, you see this nice linear correlation. Now that means, based on a turbidity measurement, which reflects the total suspended solids, you can possibly assess the titanium concentration, and if you now can relate the titanium concentration to a number concentration, if we can convert it to a number concentration, we may eventually assess the flux of nanomaterials coming out from a landfill. Now, this is the bulk concentration. If you want to get more detailed, information about the properties of the individual particles, we need to go to a spatially resolved technique, and that's the electron microscopy. My favorite slide about to show you that the strength of the electron microscopy is shown here. That's just a natural that's a natural particle, and you immediately see this is the size. The scale bar is about 500 nanometers here. The particle would be classified as probably a micron-sized particle. However, if you look at it with the TEM, with the transmission electron microscope, you see there's this fluffy materials. That's basically organics. Then you have these larger particles here, basically a clay mineral probably. And you have individual nanoscale, nano-sized materials. These are these dots here in the nanoscale, which are silicon dioxide. That immediately shows you, if I give you just a size of the particles which you would get when you do a light scattering experiment, I think you wouldn't come up with this structure of the material. And that shows you the strength of the electron microscopy. However, there's also a word of caution. And that's from a famous textbook from Williams and Carter, stating when we see this image, we laugh because we understand the 3D nature of the true 3D nature of the image. However, when you see the equivalent but more misleading images in the TEM we publish, and I think the statement can equally be transferred to the nano analytics that we're currently doing. We're getting out some numbers, but we don't understand the numbers, but we publish them. And eventually we may understand the numbers, but then we may laugh about it. So, but why do we use the electron microscopy? And I'll just show you some basic things about electron microscopy. Well, for sure, at one stage, we can't get into the nanoscale with optical microscope simply because we have a diffraction limit. We are limited in resolution. The diffraction limit is given here for optical microscope light optics, basically half of the wavelength, it's numerical aperture, which can be assumed 1 in an optical microscope. If you use green light or if you use white light, you are stuck at about 200 nanometers in resolution, diffraction limit. So what you can do is just simply go down with the wavelength. You use electrons instead of visible light, and then you can get into the sub-nanometer size range. Just to give you a flavor about the wavelength in the electron microscope, you see it's inversely correlated with the energy, with the acceleration voltage in the electron microscope. For scanning electron microscope, which are mostly operated at a few kilo electron volts, you have a few tens of picometers. For the transmission electron microscope, operated in the hundreds or 300 of kilo electron volts, we have a wavelength of a few picometers, and this definitely explains why we are much better, why we can increase the resolution. And here, just briefly, I just want to make the distinction between two families of electron microscopes. The ones are the conventional electron microscope, which can be compared with an optical microscope. And here you have a parallel illumination. It means you have the electron gun here, and then you have electromagnetic lenses that make you a parallel beam. You irradiate your sample, and you can imagine when you have material, then the electrons don't get through. The projection will be dark. When you don't have material, the electrons will go through, the projection will be white, the projection will be bright. That's why it's called a bright field image. And then, after the electron beam goes through the sample, things here, the projector lenses, they are just there to magnify the image. The important thing is that you have a direct ray path between every point of your sample and the corresponding image. That's fundamentally different if you go to a scanning version. In a scanning version, you focus the electron beam on a point of your sample. There you have a lot of interactions, creating a lot of signals. You detect the signals, and a pixel of your screen is then modulated according to the intensity of the signal that you detect. And that means you scan your sample, you scan on your TV screen, and you modulate the intensity on your TV screen according to the signal intensity you detect by this detector here. There's many different signals that you can detect, and that's just a selection here. Most important in the scanning electron microscope are backscattered electrons, give you an indication about density contrast. The secondary electrons give you an information about the morphology, topography of the sample. I'll talk about this a bit later. In the transmission electron microscope, or if you use a transmission detector, elastically scattered and inelastically scattered electrons are important too, which also give you some analytical information. Now I'd like to show you what we can do with the backscattered electrons. That is an example is shown here. That is from a filter where I filtered the effluent of these of the landfill on a polycarbonate filter. The backscattered electron reflects density contrast, so all the white areas or the bright areas are particles. You can detect them automatically and do an elemental analysis of all these particles. For example, this particle here, you have all the morphological information, you have the chemical information. It's a titanium dioxide particle. Now we can run this analysis automatically and overnight, and then we can extract the data in the morning, and these are the colors correspond to different filters, so 10 different filters, and that's just the size distribution of the particles from about 10 microns to about 200 to 300 nanometers, showing you a power law distribution of the frequency with increasing particle numbers with decreasing particle diameters, as you would expect. Important, the nice thing is now I can select just the titanium dioxide, the titanium containing particles or the titanium dioxide particles, and extract the particle size distribution as shown here. And I also see here I have a comparable size distribution that about 1% of all the particles are titanium dioxide. Important is here we see this exponential increase, this power law increase, so there's that we have reason to assume that we also have particles in the nano range. To access these particles in the nano range, we go to the transmission electron microscope. For that purpose, you first want to get rid of the large particles, just look at the small particles. You can do this with the centrifugation, and you know centrifugation depending on the density contrast, on the speed, and on the size of the particles. And if you choose the right conditions, you can select or you can deposit larger particles while smaller particles still remain in the supernatant. If you look then at the deposited particles, which we then put on the TM grid, under the TM image using a high angle annual dark field detector, that's basically a detector which strongly reflects elemental contrast or density contrast, we find different types, different morphologies of titanium dioxide particles. Here, the classical morphology of a white pigment, so that would be an engineered particle. That's more with clear crystal facets. That's probably more a natural particles, but it's the same. It's also titanium dioxide particles. And that shows us, well, it's probably not enough if we want to quantify engineered nanomaterials. We can't just use the size, because we also have natural particles in the same size range with the same chemistry, which probably is challenging to quantify. Just an example, how can we use the secondary electron image and the high angle image to get the structural relations between the titanium dioxide particles and the natural colloids. Shown here, I said the secondary electron image gives the information about the topography, the morphology of the particle, while the high angle image gives you an indication of the density. So you look through the particles. Here you look on the particle, here you look through the particle. If the particle is on the surface, the two images correspond, but they do not, because you see these particles here, you don't see them here. And that means they are incorporated in the matrix of this particle here, which probably is a flake of a paint fragment. If we then do the elemental analysis here of these particles, shown here, you see it's clearly titanium dioxide, white pigment from the paints. So now we know we have a number of particles in the sub 100 nanometer, in the larger than 100 nanometer size range. We have particles in the nanometer size range. We want to get a handle on how many particles, how many nanoparticles do we have there, how many titanium nanoparticles do we have there. And the method to assess this is the single particle ICP-MS. Just very briefly, what you do, you nebulize or you spray your sample, you aerosolize your sample, and then you count, you basically integrate what's coming out here. It goes into it will be ionized, and you count the ionized for a certain amount of time. When you do it in the classical mode, you average over long times because you want to get an average signal. When you go in single particle mode, you have very small integration times in the order of a few milliseconds, classically 5 to 10 milliseconds. Also newer devices are faster. What you do then, what you have then, or what you aim for by adjusting the dilution, you have a package where you analyze where you have no particles, then you have a particle, and you have no particle. This creates you a spike in the signal, and now if you do the calibration using the particulate standards, you can relate the height of this spike to the particle size, and you can relate the frequency of the spike to the particle number, and therefore you get some sort of a handle of particle number and particle size of certain elements, of certain particles in your sample. We did this, and it's shown, and it comes up as follows. We see we have titanium-48 that we tracked here. We have individual spikes here, and if we convert them into mass and number concentrations, we see this is on the log scale here, the number concentration. It's about 10 to the power of 4 particles that we have there. And remember, I said in the beginning, in natural waters we have about 10 to the power of 12 particles per liter. That's per milliliter, so that would 10 to the power of that would be 10 to the power of 7. Still 5 orders of magnitudes below what we have in natural surface waters. The number, the size is in the order of 150, average size in the order of 150 nanometers, which nicely corresponds to the qualitative data that we got from the electron microscopy analysis. So eventually, if you combine now all the methods, and you see the bulk titanium concentration, you see the bulk titanium concentration, and you see the elemental or the size distribution from the scanning electron microscope, the qualitative information from the transmission electron microscope, and the number distribution from the single particleized PMS analysis, you probably can come up eventually with defining or assessing some fluxes of engineered materials coming out of the landfills. To conclude, I showed you in the beginning, we have several analytical techniques which are available to characterize materials, but most of them, or I would say all of them, they fail if we have complex matrices. We will have complex matrices, that's a fact, but there will be no general protocol how to deal with these samples. We have to develop our preparation methods according to our needs, and I think the most important thing is that we have to formulate our questions, and based on this we get the analysis and not the other way around. With these words, I'd like to conclude my talk and thank you for your attention. Maybe I left some time for questions.